Today we're going to be talking about Thevenin and Norton equivalent circuits, specifically for circuits that do not contain dependent sources, and we're going to cover what happens with dependent sources on Friday's lecture. So long I can't even spell circuits. All right. So the first thing that we're going to talk about here is Thevenin's theorem. So Thevenin's theorem states that any linear two-terminal network can be replaced at the terminals by a Thevenin voltage source VTH in series with a Thevenin resistance RTH. So effectively, Thevenin's theorem says that we can replace any linear two-terminal network with a practical voltage source, just a voltage source in series with a resistance. So now we need to talk very briefly about how to determine the Thevenin voltage and how to determine the Thevenin resistance. Okay? So the Thevenin voltage is the open circuit voltage measured across the terminals of the live network where a live network is simply one in which all of our independent sources are left on. And the Thevenin resistance is the resistance seen between the terminals of the dead network, where a dead network is simply a network in which all of the independent sources have been turned off. So we are going to put this into practice by looking at a circuit. So this will be our circuit of interest. Let's put a 2 ohm resistor here. 4 ohm resistor here. Let's make this a 3 amp current source. Let's make this 6 ohms, sorry. 8 ohms. 10 ohms. And I'm going to draw a pair of terminals here. And let's make this a 1 ohm resistance here. And so our goal is to find the Thevenin equivalent circuit with respect to that 1 ohm resistor. So effectively, we're going to find the Thevenin equivalent circuit of everything to the left of those terminals that I drew. So this is going to consist of 2 steps. We need to find our Thevenin voltage, and then we need to find our Thevenin resistance. Okay. So let me write here, find the Thev equivalent circuit with respect to the 1 ohm resistor. All right. So finding our Thevenin voltage, we were already told how to do it, okay? So we were told that the Thevenin voltage is the open circuit voltage measured across the terminals of the live network. Since we're finding the Thevenin equivalent circuit with respect to a particular element, we need to take that element out of the circuit so that it doesn't influence our measurement. So I'm going to redraw my circuit, and I'm just going to leave the 1 ohm resistor out. So now I have an open circuited set of terminals, and my Thevenin voltage is simply the voltage drop across these open circuited terminals. Now, I arbitrarily chose to put the positive polarity terminal on top, the negative polarity terminal on bottom. In your homework assignments and exam questions and all that kind of stuff, I will explicitly tell you the positive polarity reference will be on top, right, etc., all that kind of good stuff. So you'll always be told where to put your positive polarity terminal for your Thevenin voltage. That being said, it doesn't particularly matter as long as you're consistent about things, stuff's going to work out okay. All right, so it's 8:10 in the morning, 2 weeks after you guys have done any circuit analysis whatsoever, I'm assuming. How do you think we should analyze this circuit to find VTH? Somebody suggest something. So I heard source transformation, and I would argue that there isn't a source transformation that can be done, at least not without doing some simplification, right? So in order for us to do a source transformation, our 3 amp current source would have to be in parallel with a resistance. At present, it is not in parallel with any resistance. However, if we were to combine the 4 ohm resistor and the 2 ohm resistor into a 6 ohm resistor, it would then be in parallel and we could do a source transformation. So that's definitely one route that we could go. Yes. Mesh analysis is definitely another route that we could go. Neither of those are the 2 routes that I would personally choose. So since the first suggestion was a source transformation, let's explore that and then I'll tell you how I would do it. Okay. So I'm going to combine my 2 ohm resistor and my 4 ohm resistor into a single equivalent resistance of 6 ohms. And now I have 3 amps in parallel with 6 ohms. So that is going to look like 18 volts in series with 6 ohms, right? So that would be something like this. And then we have this 6 ohm resistor. This 8 ohm resistor. This 10 ohm resistor. And then this is the VTH that we're looking for. So whoever suggested a source transformation, tell me what my next step should be. Because we made the circuit different, but we certainly didn't solve for VTH. You're doing way too much work. So let me ask you a question. How much current flows through the 10 ohm resistor? What? 0, because it's not part of a closed current carrying loop, okay? Since no current flows across the 10 ohm resistor, we can see by inspection, so I'm going to write here, this current has to be 0 amps, which means this voltage has to be 0 volts, which means the Thevenin voltage is just the voltage drop over the 8 ohm resistor. So what would be the easiest way to find the voltage drop across the 8 ohm resistor for this particular circuit? Voltage division, thank you. So we could see that VTH is going to be 18 volts times 8 ohms over 6 ohms plus 6 ohms plus 8 ohms. So that's going to be 18 times 8 over 20 is 36/5 of a volt. Now let's take Patrick's suggestion and use mesh analysis. So going back to our original circuit, I'm going to define this to be mesh 1, this to be mesh 2. So I can see that I2 minus I1 is equal to 3 amps. And then I'm going to lump some things together here. 2 ohms plus 4 ohms looks like 6 ohms times I1. 6 ohms plus 8 ohms looks like 14 ohms times I2 is equal to 0. And then I can solve this system for I1 and I2. So let's do just that. So let's see, my coefficient for I1 in my first equation is -1. My coefficient for I2 in my first equation is +1. My constant term is +3. Then I have 6 I1, 14 I2 is equal to 0. Solving, I get -21 over 10 amps and +9 over 10 amps. From this, VTH is just going to be 8 ohms times 9/10 of an amp. which gives me the same 36/5 of a volt. So two different ways, got the same answer. So this is actually leading us to something important here. When finding the Thevenin equivalent circuit, it really doesn't matter what technique we use, as long as we're doing the right thing, finding that open circuit voltage, whatever we're comfortable with will get us where we need to be. Now, from efficiency's sake, let me show you the way that I would work this problem. So starting with our original circuit, so the first thing that I notice is that there's no current flowing through the 10 ohm resistor, so there's no voltage drop across the 10 ohm resistor, something that we've established in our previous two analysis as well. So what I'm going to do is I'm going to use a combination of current division and Ohm's law in order to solve for VTH in a single calculation, right? So my goal is to figure out what current is flowing to the right. So I'm going to call this I sub R. And then whatever that current is times 8 ohms is going to give me my Thevenin voltage. So using current division, we could say that VTH is going to be 3 amps times 1 over 6 ohms plus 8 ohms divided by 1 over 2 ohms plus 4 ohms plus 1 over 6 ohms plus 8 ohms. So this part right here is giving me the current IR. And now I'm just going to multiply this by 8 ohms, which will give me the voltage that I'm looking for. So let's throw this into my calculator and make sure that I'm thinking about things correctly. So 1 over 14, 1 over 6, plus 1 over 14 times 8 is 36/5 of a volt. Did everything in a single calculation. So nothing wrong with the other ways, but it's not as efficient as it could be. And when you guys are faced with problem like this on your exam, where you've got 25 questions to work in less than 2 hours, efficiency is going to be key. All right, so we've solved for the Thevenin equivalent voltage 3 different ways. There are other ways that we could do it. We could use nodal analysis and solve for it directly. Can't really use superposition or anything like that because there's only a single source. Yeah, I think those are pretty much 4 different ways that we could have thought about this. All right, so now we're going to find the Thevenin resistance. So to find the Thevenin resistance, we look at our dead network, which means we turn our independent sources off, and then we're just going to look through the terminals, our open circuit terminals that we found VTH at, right? So that's going to look something like this. So here's our 2 ohm resistor. Four ohms. These are the terminals where my current source was. Remember, to turn a current source off, we open circuit it. So I now have two sets of open circuited terminals. Which ones am I looking into to find the Thevenin equivalent resistance? The right side, yeah. So I'm going to look in here and find RTH, okay? Because we're finding the Thevenin equivalent resistance with respect to the 1 ohm resistor, we need to look in the open circuited terminals left behind when we took the 1 ohm resistor out. The fact that there's a second set of open circuited terminals because we had to turn off that current source is completely immaterial to what we're looking for, okay? So what resistance do I see? Infinite? I very much disagree. There's a simple resistor network there that I can simplify. So 2 in series with 4 is in series with 6, and that's parallel with 8. All right, so that's going to be part of it. The 10 is going to be in series with that equivalent resistance. Absolutely right. So this is going to look like 10 plus 8 in parallel with 2 plus 4 plus 6. So let's see. So that's going to be 10 plus 8 times 12 over 20. (74/5) of an ohm. Ashton, did I do mental math correct? 2 plus 4 plus 6 is 12, and 12 and 8 is 12. So yeah, there. All right. So finding the Thevenin resistance is literally just using resistance combination techniques like we've been doing for the better part of a month and a half or whatever in this class, or I guess a month. And you've been doing it in previous classes and all that kind of jazz. So putting this together, we can say that this circuit, where we have 2 ohms in series with 4, 3 amps, 6, 8, 10, 1 ohm here, is electrically equivalent to this thing. We have replaced everything to the left of the terminals of the 1 ohm resistor with its Thevenin equivalent circuit. Why might we be interested in a Thevenin equivalent circuit? Because it gives us an easy way to determine the power, right? Because now we have a very, very simple circuit to analyze. So in industry, Thevenin equivalent circuits are used for power analysis, particularly when you're trying to make sure that you're not going to burn out a particular element or something like that. So we're trying to make sure that the ratings of that element are not exceeded, but we are going to use it as an analysis technique. We're going to use it later on, like right now, it's its own kind of thing that we're solving for, but later on, we're going to use it to simplify circuits as well. All right, so this is an example of Thevenin equivalent circuits, finding the Thevenin equivalent with respect to a particular element. After we talk about Norton equivalent circuits here in just a moment, then we'll circle back around to finding the Thevenin equivalent circuit with respect to a set of terminals, which is roughly the same thing. We just don't have to take an element out. So Norton's theorem. Norton's theorem states that any linear two-terminal network may be replaced at the terminals by a Norton current source, I Norton, in parallel with a Norton resistance, R Norton. Or effectively, Norton's theorem states that we can make any two-terminal linear network look like a practical current source. The Norton current is the short circuit current flowing through the terminals. And the Norton resistance, through the terminals of the live network. And the Norton resistance is the resistance seen between the terminals of the dead network. So the Norton resistance is literally the exact same thing as the Thevenin resistance, so you will never hear me refer to it as a Norton resistance again. It is literally the same thing, defined in the exact same way, determined in the exact same way. There is no need to have two different quantities. It's the same damn thing. All right, so let's take our circuit from a moment ago. And now find the Norton equivalent circuit. The only thing that we're really going to have to find here is the Norton current, because we already know what the Norton resistance is from our previous one. All right. So to find I Norton, we're going to draw our circuit with the 1 ohm resistor taken out, just like we did with the Thevenin equivalent circuit. So here's our circuit with the 1 ohm resistor taken out. Now we are going to short circuit those terminals, and we are going to find current flowing through the short. That will be our Norton current by definition. So how do we want to find this short circuit current? So two methods jump out at me, both of roughly equal difficulty and involvement. The first one is doing current division twice. So effectively, if I can find the current that flows through this branch, I can then see how much of it splits up and flows through this branch. Or I could just do mesh. Either of those methods will probably be the easiest. That being said, I could do a source transformation and go through whatever that entails as well, but probably not going to be as efficient as either current division twice or mesh analysis. So what floats you guys' boat this morning? Current division twice. Okay. I wish I had not erased that thing. So I'm going to call this current IX. And then this current IY. Okay? And IY is the exact same thing as I Norton. So I guess I could actually just leave it as I Norton. But anyway. So let me think about things here. I'm considering doing it all in one step because I'm lazy and it's possible. Would you prefer me to break it into two distinct steps? Okay, let's do it that way then. So IX is going to be 3 amps. I'm trying to find the current that's flowing to the right. So to the right, I have a resistance of 6 ohms in series with 8 in parallel with 10. So I'm just going to write that as 8 in parallel with 10 like so. And then I'm going to have 1 over 2 ohms plus 4 ohms plus 1 over 6 ohms plus 8 in parallel with 10. And that's going to give me a number. Let's figure out what that number is here really quickly. One over, let's see, 6 plus 80 over 18. 1 over 6 plus 1 over 6 plus 80 over 18. I got 81. Excuse me, over 74 amps. And from here, I know. Yes. So the total resistance in parallel to the right that is in parallel with a 3 amp source is 6 in series with 8 in parallel with 10. Yeah. And then let's see. So I Norton is going to be IX times 1/10 over 1/8 plus 1/10. So bless you. $18 over 37. Amps is what I got doing this way. You guys want to verify using mesh? Okay. So using mesh analysis, This is our circuit. This current is I Norton. I1, I2, and I3. So we can see directly that I Norton is the same thing as I3. So we are going to have, let's see, I2 minus I1 is 3 amps. 6 ohms times I1 plus 6 ohms times I2 plus 8 ohms times I2 minus I3 is equal to 0. So that's our KVL equation around our super mesh. And then lastly, 8 ohms times I3 minus I2 plus 10 ohms I3 is equal to 0. Let's solve this system for I1, I2, and I3, which is the same as I Norton's. So I have a 3 unknown system. So in my first equation, my coefficient for I1 is -1, my coefficient for I2 is +1, my coefficient for I3 is 0, my constant term is 3. In my second equation, my coefficient for I1 is 6, my coefficient for I2 is 14, my coefficient for I3 is -8, my constant term is 0. In equation 3, my coefficient for I1 is 0, my coefficient for I2 is -8, and my coefficient for I3 is 18. And let's see, for I1, I got -141/74. For I2, I got 81/74. And for I3, I got 18/37. But once again, both ways got us the exact same result, reinforcing the fact that you can just do whatever you're comfortable with and you'll wind up getting the right answer eventually. But think about how to do things as efficiently as possible. All right, so we already know that R Norton is equal, RTH was 74/5 of an ohm from our previous work. So we could say that these two circuits are electrically equivalent as well. 18/37. All right, so if the Thevenin equivalent circuit is equivalent to everything to the left of the 1 ohm resistor, yes. Realistically, yeah. So like, would this circuit change at all if I turned everything upside down? Not even a little bit, because everything would change, right? So it doesn't particularly matter now. All right, so if the Norton equivalent circuit is equivalent to everything to the left of the 1 ohm resistor, and the Thevenin equivalent circuit is equivalent to everything to the left of the 1 ohm resistor, then it seems fairly obvious that the Norton equivalent circuit and the Thevenin equivalent circuit are electrically equivalent to each other. So realistically, the Norton equivalent circuit is just the source transformation of the Thevenin equivalent circuit and vice versa. And we can prove that very, very easily, right? So we know from source transformation that Vs should be equal to Is times Rs. So this should extend to say that V Thevenin should be equal to I Norton times R Thevenin, or I Norton would be V Thevenin divided by R Thevenin, or R Thevenin would be equal to V Thevenin over I Norton. So we can check this very easily because we know all three of these parameters because we solved for them all, right? So just as a quick check here, 18 over 37 times 74 over 5 comes out to be 36 over 5, our Thevenin equivalent voltage that we found at this point 20 minutes ago, right? So technically speaking, at least for circuits like this, where we don't have any dependent sources to worry about, if we find two of the three quantities, we can easily find the third one and be pretty damn assured of our work. And worst case scenario, we can solve for all three things as a means by which to check to make sure we've done everything correctly. All right, so let's work another example. But in this case, I'm going to find the Thevenin equivalent circuit with respect to a set of terminals. And literally the only thing that's going to change about this process is that I don't have to take the element of interest out because we already have an open circuit to deal with. Okay. So let's say that I have this circuit. I have a 4 ohm resistor in series with a 6-volt source. Here's a 2 ohm resistor. Make this a 5 ohm resistor. 3 ohm resistor. 8 ohm resistor. 12-volt source. And then across the top, let's put a 2 amp source like so. I'm going to label this terminal A and this terminal B. And I want to find Thevenin and Norton equivalent circuits with respect to terminals A and B. So let's assume positive is at terminal A and I Norton is now. So which quantity do you guys want to solve for first? Combine the Thevenin voltage, Thevenin resistance, or Norton current. Any one of those three. Resistance is probably going to be the easiest thing. Sure, let's solve for it. Okay. So finding our Thevenin equivalent resistance, we need to be looking into a dead network, which means we turn off all of our independent sources. So my 2 amp source is going to be open circuited. My 6-volt source is going to be short circuited. So here I'm going to see a 4 ohm resistor. Two ohm resistor, 5 ohm resistor, 3 ohm resistor, 8 ohm resistor, And because I'm finding the Thevenin equivalent circuit with respect to terminals A and B, I need to look into terminals A and B. So what do I see? So the 4 and the 2 are in series. I agree with that. That combination is in parallel with the 5, which is in series with the 3, which is in parallel with the 8, right? So it's going to look like 8 ohms in parallel with 3 ohms in series with 5 ohms in parallel with 2 ohms in series with 4 ohms. So let's see. 8 ohms times 3 plus 5 times 6 over 5 plus 6 divided by 8 plus 3 plus 5 times 6 over 5 plus 6. Times 3 plus, let's see, 30 over 11. Plus 3 plus 30 over 11. I got 504 over 151 if I did this correctly. If I believe I did. All right. So we found RTH, arguably the easier thing. Now, what do we want to solve for? VTH or I naught? Thevenin voltage, okay? So, here. I'm going to be lazy and also I can't remember all of this. And so I'm just going to copy this thing. Good deal. Thank you, Ash. All right. So while you guys are copying that circuit down, think about what analysis method you would prefer to employ to find the quantity VTH. Anyone have any thoughts? All right, so let's run through some things. This circuit is fairly complicated. So there's not anything obvious that's screaming KCL, KVL, Ohm's law, voltage division, or current division. All those are kind of out the window for a circuit this complicated, which means we really have to choose between nodal and mesh. So let's talk through that, right? So if we look at this circuit, 1, 2, 3, 4, 5, 6 nodes. However, there are 2 voltage sources. So if we were to choose the bottommost node as ground, 2 of those nodal voltages are actually, the ground would also be known. So 3 of those 6 nodes, we have a specific voltage source. So it's going to be a 3 equation, 3 unknown system. and we would be able to solve for VCH directly. Nodal analysis, we can see very easily that there are three meshes. So we could solve for our mesh current, and then we could mesh currents, and then the voltage VTH would just be the voltage drop across the 8 ohm resistor plus the voltage drop across the 12 ohm resistor. So it wouldn't be the same level of difficulty, three equation, three unknown system, but then we have to do one extra step at the end, which to me means it's slightly less efficient than just doing nodal analysis. So I'm going to choose to do nodal here, even though it looks like it's going to be more difficult, because I'm going to have so many known voltages that I get to deal with, right? So this will be my ground. And then here's VA, VB, and VC. And these are the only three that I'm going to bother to label. We're just going to leave. Well, we know that this voltage here at this node is 6 volts. And we know that the voltage here at this node is 12 volts. So we're just going to substitute that in directly, right? So KCL at A is going to look like VA minus 6 volts over 4 ohms plus 2 amps plus VA minus VB over 2 ohms. KCL at node B is going to look like VB, let me write that down. VB minus VA over 2 ohms plus VB over 5 ohms plus VB minus VC over 3 ohms. KCL at node C is going to be VC minus VB over 3 minus 2 amps plus VC minus 12 over 8. And now I'm just going to solve this three equation, three unknown system for VA, VB, and VC. So in my first equation, later on, my coefficient for VA is 1/4 plus 1/2. My coefficient for VB is negative 1/2. My coefficient for VC is 0. And my constant term is going to be 2 plus 6 over 4. In my second equation, my coefficient for VA is negative 1/2. My coefficient for VB is 1/2 plus 1/5 plus 1/3. My coefficient for VC is negative 1/3. My constant term is 0. I actually made a mistake in my first equation. I said my constant term was going to be 2 plus 6 over 4, but it should be negative 2 plus 6 over 4 because I forgot to change the sign on that 2 when I moved it to the other side. So let me fix that. So negative 2 plus 6 over 4. All right, sorry about that. For KCL at node C, my third equation, my coefficient for VA is 0. My coefficient for VB is negative 1/3. My coefficient for VC is 1/3 plus 1/8. My constant term is going to be positive 2 plus 12 over 8. Solving this system, I get VA to be 386 over 151. VB to be 730 over 151. Action, did I screw something up? I'll run back through it here in a moment. And then VC will be 1684 over 151 volts. And if I did this correctly, this is the Thevenin. So because Ashton and I got different results, I'm going to run through that system again just to make sure. All right, so first equation, my coefficient for VA is 1/4 plus 1/2. My coefficient for VB is negative 1/2. My coefficient for VC is 0. My constant term is going to be negative 2 plus 6/4. For my second equation, my coefficient for VA is negative 1/2. My coefficient for VB is 1/2 plus 1/5 plus 1/3. Okay, so I'm going to stop it. All right. It's always a crapshoot, and actually, probably I'm going to get it wrong more than Ashton does because she's paying more attention than I am. That's okay. All right, so we found our Thevenin voltage. We found our Thevenin resistance. So from here, we can find our Norton current just by simply taking the ratio of these two quantities. Or we could find our Norton current directly and then use that to check our work. Which route do you guys want to go? You want to check stuff, or do you want to say, I'm done listening to this jackass talk for the day? Let's check it. Okay. So finding I Norton. So we're going to short circuit things here. We're going to find this short circuit current. So we very obviously have 4 meshes. However, we have a current source on the perimeter of the circuit. So one of our currents is going to be a known quantity. So we're once again going to have a 3-equation, 3 unknown system. So we should be able to do this on any of our calculators. So let's call this I1, I2, I3, and I4. We know from the jump that I1 is 2 amps. So now let's look at KVL at mesh 2. So that's going to look like negative 6 volts plus 4 ohms times I2 plus 2 ohms times I2 minus 2 amps plus 5 ohms times I2 minus I3. This is all one long equation. Set that equal to 0. KVL at mesh 3 is going to look like 5 ohms times I3 minus I2 plus 3 ohms times I3 minus I1, where I1 was 2 amps, plus 8 ohms times I3 minus I4, plus 12 volts is equal to 0. And then lastly, KVL at mesh 4, negative 12 volts plus 8 ohms times I4 minus I3. That's it, is equal to 0. All right, so we have another 3-equation, 3 unknown system. All right, so in my first equation, which is going to be my KVL at mesh 2 equation, my first variable is going to be I2. So my coefficient for I2 is going to be 4 plus 2 plus 5. My coefficient for I3 is going to be negative 5. My coefficient for I4 is 0. And then my constant term is going to be 6 plus 2 times 2. And my KVL at mesh 3 equation, my coefficient for I2 is going to be negative 5. My coefficient for I3 is going to be 5 plus 3 plus 8. My coefficient for I4 is negative 8. And my constant term is going to be negative 2 times 3. I'm reading my handwriting correctly. Yeah. Oh, and also minus 12. My apologies, I forgot that minus 12 at the end, right? So I have this current is contributing a constant term, and this voltage is contributing a constant term. I need to include both of them, or it's going to be wrong. So negative 6 minus 12. All right, in my last equation, my coefficient for I2 is 0, my coefficient for I3 is negative 8, my coefficient for I4 is positive 8, and my constant term is positive 12. Solving these, I get I2 is 50 over 63. I3 is negative 16 over 63. And I4, which is I Norton, I got to be 157 over 126. All right, so now let's check some things out. So V Thevenin should be I Norton times R Thevenin. So that would be 157 over 126 amps times 504 over 151. One five seven over 126. $628 over 151. Which I got. My current's not right. Okay. Yeah, no, that's fair. All right, what did you get for your current, Ashton? Positive? All right, so let's see if that fixes things, and I'd be willing to bet it does. All right, so scratch that out right there. So 421 over 126 times 504 over 151. 1684 over 151, which is the correct one. All right, awesome. So thank you for that, Ashton. I'm too lazy to go back and figure out what I typed into the calculator. So, as it turns out, it's absolutely fantastic to have a means by which to check our work built into this analysis tool, because even if you're a jackass with a PhD, you still make mistakes. Okay. All right, so we've talked about Thevenin and Norton equivalent circuits, all that kind of good stuff. So you're free to work on your in-class assignment. On Friday's class meeting, we are going to cover Thevenin and Norton equivalent circuits with dependent sources, and then we're also going to have a mini lab. So get to it.